Good evening, everybody. It is Wednesday night and it's time for some electricity. We're going to follow on from last week's lesson, or sorry, 2 weeks ago's lesson, where we did the basics of electricity. We started talking about current, voltage, and how we would use the equations to run those things. Okay, so now we're going to get down to the nitty gritty. We're going to get some circuit diagrams put together and we're going to work out what the voltage is like and what the current's like at different places throughout an entire either series or parallel circuit. This is by far the hardest question that you will do on your GCSE paper. No two ways about that. There's too many ways to ask it. You can't be fully prepared for it, so you've got to understand it. So let's get ourselves cracking here. We've got ourselves a little power supply and let's make ourselves a not circular circuit but a rectangular circuit, because that's what we're used to seeing, and we'll just make a little circuit like this, send that to the back so that it looks alright, right, like that. And we're going to stick a resistor here, and we're going to stick another identical resistor up here. So we're going to assume that so far, if we're looking at resistors, we're looking at identical resistors until such times as we start putting some kind of numbers on top of things. Okay, let's just assume they're identical to start with. Good to see you, Kieran. Saw your comment there. Right, so let's imagine that we have a 6-volt battery or a 6-volt power supply going on here. Okay, so what was 6 volts up there? Alright, what we really want to be able to do is answer questions where we're asked to do things like, if I put a voltmeter here, okay, and give it some legs, so a voltmeter measures what's going on with voltage between 2 points, so between that point and that point. What we want to do is want to be able to answer what's the voltage there. Okay, so for those of you who are up to date with this, hit the answer up in the chat section, see if we get that right a little bit on, and then we'll put an ammeter here, and we'll stick another ammeter here, and we'll put another ammeter up here. And normally we put little 1s, 2s and 3s below them, but because we're talking as we go, we'll be able to, so this one and this one and this one. Okay, so we need to fully understand what we're talking about in terms of voltage, and we're talking about current. So let's give ourselves a little current to play with. Let's say this current here is 0.75 amps. Okay, so when we're reading this ammeter, it says 0.75 amps. Right, so what that means, okay, following on from our thing last week, if you consider electricity to be a stream of little coulombs, so let's get some green coulombs going on, then we've got piles and piles and piles of electrons broadly grouped together into these little bundles that we call coulombs. Right, and they're all the way around the whole place, piles of them every which way, and what they do is that as one moves, the other moves, the other moves, the other moves, so we've got a continuous stream of them going round. So for every one that's moving up here, there's another one coming back through and all the way round. Okay, so we get rid of those ones and we'll just talk about this one. Now, what voltage means from last time is the voltage between 2 points is how much electrical energy is either used up or given to a coulomb between 2 points. Okay, it's the change in electrical energy between 2 points. All right, so what a 6-volt battery basically means is that it goes out into the circuit with 6 joules per coulomb, and it comes back with 0 joules per coulomb. Right, as far as we're concerned anyway. In reality that's not true. It comes back with some, but it leaves with more. But the difference between the two is 6. So you can make it 6 and 0, 7 and 1, 8 and 2. Makes no difference in terms of math. It's just much easier to say 6 and 0 because that gives you a little rule for electricity, which is you should be arriving back at your power point with 0 joules. Alright, so let's set off. What's going to happen to our little coulomb? He's going to travel around here. He's going to come through this ammeter, which he's going to completely ignore, or she. You know, we're not gender biased here at all. Travels on, we'll get beat up through this resistor. We'll travel through here, completely ignoring this because it's designed to not interfere. Up through here, we'll ignore this path because a voltmeter is also designed to not interfere with the circuit. We'll then get beat up going through this and lose some energy and arrive back with none. Now the critical point here to understand is that the amount of energy it requires to get through this depends on how difficult this resistor is to pass through. Now note what we said at the start. This resistor and this resistor are identical. So the experience this little coulomb has to get going through here has to be an identical experience as going through this resistor here. Now, there can't be a difference, otherwise these resistors are not identical. Okay, so down here we still have 6 joules because we didn't go through anything that was going to take any energy off us. And coming out of here, we must have 0 joules because the ammeter doesn't do anything. So that's what we've got so far. What we want to know is what do we have here and what do we have here. Okay, because if we know what we have here and here, then we know what the reading on this voltmeter is. Right? Now we have to lose 6 joules because we're going from 6 down to 0, and we have to lose the identical amount of energy from this one and this one because these two resistors are identical. Right? So half of your energy is going to be lost here and half of your energy is going to be lost here. So you're going to lose 3 joules going through here, and you're going to go down to 3 joules in every coulomb here, and you're going to have 3 joules coming in here because this little coulomb is going to move along, still having 3 joules, and enter here. Does that make sense? Now, I should be technical that if we're talking about, we're not really talking about joules, we're talking about joules on that coulomb, but really we're talking about joules per coulomb, right? Because every coulomb is going to experience that, and a joule per coulomb is a volt. Okay, so here it's got 6 volts, or here is 3 volts, here is 3 volts, and here is 0 volts. Right, so the reading on the voltmeter is, it tells you what's the difference in voltage between where this leg is and where this leg is. And the difference in voltage is 3 volts. So there we have it. That's what this ammeter or this voltmeter says. Now the difficult bit coming up now is, right, what does the ammeter over here say? Well, the ammeter tells you the flow of coulombs going past. All right. Now remember what we said last time, that the flow of coulombs is, you imagine that this whole thing is completely chock full, and 1 coulomb can't move until the one in front of it moves. So all the way around here, there's like the world's largest traffic jam going on. Right? And nobody can move until the dude in front moves. I can't believe I said dude. Sorry, child of the 80s. What can you do? Alright, so when this moves, this moves, this moves, this moves. So if 0.7 amps is going through here, well, 0.7 amps must also be going through here because the flow of coulombs along here must be the same, because there's nowhere for it to split off. There's nowhere for it to park up and have a nap. There's nowhere for it to spread out. It can't go along here because the voltmeter, like we said, is designed to not interfere. Right? So that means that this one has to be 0.75 amps. And this one here has to be also 0.75 amps. All right, and this is a rule for series circuits. In fact, there are 2 rules for series circuits. One is that the voltage is shared between components. All right, and that it's not shared equally. Notice there's no shared equally. In this case it is because they're identical, but if this one was much more difficult to get through, which we'll do soon, then it'll take more energy to get through than this one. And 2, the current is the same everywhere. Right, these are 2 critical rules for series circuits, and this is just for series. Is that all right? Okay, cool. So let's get ourselves cleared up a bit here, and let's try something a little bit more technically difficult. Okay, so what we're going to start doing here is we're going to start introducing some numbers. Okay, we could do it by letters, but we'll get you introduced to the number systems first. Okay, so let's get rid of all this stuff. So away it goes. There we are. So delete all that out, and let's move a bit of stuff around. Okay, so we'll take out that ammeter, but we'll add in another voltmeter, because we're really going to play with the idea of voltage here. Because current's not interesting in a series circuit, even a little bit, because it's the same everywhere. So once you've got one, you've got them all. It's like the worst game of Pokemon ever. And then let's change our battery up here. Let's give that let's give it an 8-volt battery. Not that you see too many of them about, but it's good to not just keep using the same numbers over and over again. All right. So what we can say here is that our coulomb entering into the circuit has 8 joules, or is considered to be an 8 volts point there, and coming back we're going to have 0 volts, right, which gives us our voltage difference going on. Alright, nice one. Apologies for the random misclick there. Okay, but now let's pop a number or 2 in here. So let's say that this is 20 ohms, and that's the measurement of resistance. And over here, let's say that we have, let's say 60 ohms. So this is a 60 ohm resistor. I'll spin that round so that it fits inside the resistor. Okay, so we've got a 20 ohm and a 60 ohm resistor. And what we want to know is what are the readings in these two voltmeters, and what's the reading on this ammeter. Now, that could be interesting. All right, so let's take care of the voltage first. Okay, there are a couple of ways we can do this, but we're going to do it kind of logically first of all. So our little Coulomb arrives around here with its 8 volts. Right, and it's going to come out of this 60 ohm resistor with 0 volts. Now the automatic instinct is to go 4 and 4, but that's not true, because this little Coulomb, as it comes through this 20 ohm resistor, is going to have a much nicer time than when it comes through the 60 ohm resistor, where it's really going to get messed up. So it's going to need a lot of energy to get through this and less energy to get through this. But how much energy is the question? Well, the answer is simply in proportion. That this one is 3 times as difficult to get through as this one. That's what the number's for. Okay, so what we have is we have a ratio. We have a 20 to 60 ratio. There's 20 ohms for 60 ohms. That reduces down to a 1 to 3 ratio. Okay, and in a 1 to 3 ratio, that means you have 4 parts. Okay, and those 4 parts are going to have to be divvied up to make up the whole 8 volts. Right, so once we divvy this up, kind of 1 part to 3 parts, that's going to be the whole 8 volts used up. So 4 parts is 8 volts. Divide both sides by 4 gives you 1 part equals 2 volts. All right, and then 3 parts is equal to 60 volts, or sorry, is equal to 6 volts. Okay, so the 1 to 3 ratio is the resistance is 1 to 3. So the 1 part gets 2 volts. So down here, this is going to use 2V. And over here, this is going to use 6V. Okay, so that's how we get this. Okay, we simply use ratios between these two, and if there were 3, you could do exactly the same thing in 4 and 5 and so forth. All right, now we want to get the current that's going through this ammeter, and this is where people struggle. Okay, see this all the time. Really clever students go, right, how the heck do I get that? And what they need to realize is they don't actually want the current going through here. They want the current anywhere, because it's a series circuit. So where can we get the current? And we can get the current through here. All right, because what we can use is we can use Ohm's law, that V equals IR. And through this resistor, we happen to know that 2 volts of voltage is being used is equal to I, which is the current, we don't know that, multiplied by 20, which is the resistance. All right? Dividing both sides by 20, we then get 0.1 equals I. And a final answer then of the current is equal to 0.1 amps. And now we haven't found out what's going on here, but we have definitely found out that going through this resistor is 0.1 amps. And since this is a series circuit and the current is the same everywhere, that means that the current going through this ammeter is 0.1 amps, and of course, therefore over here, it's also 0.1 amps. And just for the sake of completeness, just to show that we could have done it anyway, we could have used this bit here, right, and tried to work out what's the current going through the other resistor, and we would expect to get the exact same answer. And in that way, we have V equals IR. And in this set of resistor, we have a voltage of 6 is equal to a current that we don't know, multiplied by a resistance of 60. And again, dividing both sides by 60 this time gives me 0.1 equals I. Exactly what we would expect. Okay. Quick check in the comments. Good evening, JD. How's things? Do we have to do the tracker, Kieran? You've done the tracker, so you're all right for the minute. Okay. Happy people, I hope. So that's how we calculate current and voltage within series circuits. And then we want to make the game an awful lot more fun by talking about parallel circuits. So let's clear up a bit. And let's get some different stuff going on here. Right, so get rid of all of this McGubbins, because it is parallel circuit time, and you can sense the excitement throughout the entire of the internet for this. Right, so we're going to change again our battery. We're going to change that to, let's change that 9 volt battery, a little bit more common. Grab our wee Coulombs, stick him up there. get rid of this gear and get rid of this. Yeah, we want to get rid of that. Okay, so let's take out a resistor and move our voltmeters out of the way and take off all this extraneous stuff. Okay, and now let's mess with some people. Right, so let's go. We'll put a resistor there, and we'll start simple. So we'll just do a simple branch off here, and we'll stick a resistor on that path. And then we'll maybe want to know what the voltage is going through that bit. We'll probably want to know what the current is as well. So we'll bring that to the front. Order bring to front. Oh, I need to fill that in. Whoopsie doo. Didn't want to fill that in. Doing well here so far. Oh, there. Hope that's right. There we go. Okay, so we've got our ammeter stuck on that corner, and we want to see what's going on there. So let's give some numbers here. Let's give you another ammeter up here, and let's tell you that the current going through this ammeter is 0.5 amps. Okay, so this ammeter reads 0.5, and we'll connect up our voltmeter because it would be rude not to. We'll have our voltmeter tell me, right, what's going on between here and here. Alright, so this looks, on the face of it, reasonably difficult. We're not giving any numbers, we're going to assume that these are equal in the first place. So once again, if you're reasonably confident with this, what are your predictions in the comments section? And we know that we're coming out here at 9 volts, and we're coming back here at 0 volts. And provided you keep remembering that, you will do quite well at electricity. So we travel around to here, arrive here, and we know we're dealing with a parallel circuit because I could go this way, or I could go this way, and there's nothing stopping me doing either of those things. So you've got a choice, and once you've got a choice, you've got parallel circuit systems going on here. I'm going to get rid of these series circuit rules so that people don't get confused. So we arrive here with 9 volts. There's nothing whatsoever to be done here, so we know we're coming out of here with 0 volts. And here's the trick, right? That I could go through this way and out there, and I could go through this way and out there, and some of my coulombs will go this way and some of my coulombs will go this way, right? And when they do, if you come from here at 9 volts and you come out of here at 0 volts, you will lose 9 volts going this way, right? So this one here, this bottom one, will lose 9 volts. But also, this top one up here will also lose 9 volts. Okay, so no matter which branch I take, and this is called branching, so I take this branch, or this option, or I take this option, no matter which option I take, I'm going to end up losing the exact same amount. I'm going to lose 9 volts going this way, or 9 volts going that way. The voltmeter is saying, what's the difference between here and here? Well, I go in with 9, and I come out with none, so my voltmeter says 9 volts. All right, and this is one of our primary rules for parallel circuits. In parallel circuits, the voltage across each parallel branch is the same. Okay, now notice that's for the whole branch, not for each component, and we'll make life a little bit more complicated shortly. But there's a trade-off. Okay, and the best way to think of this, I like thinking of this in terms of water. If you imagine that you had a little river, so you're above a river and you're watching it flow along. Okay, so we get a little highlighter, highlighter pen. Oh, we've got blue, right? So little river, flowy, flowy, flowy. All right, and it's flowing down the page like this. Okay, at some point later on down, the river splits. Okay, and it splits into 2 separate streams. Right, some of the water is going this way, and some of the water is going that way. That's completely not controversial in the slightest. Okay, everybody can accept that as a thing. The same thing is going to happen to your coulombs. Some of the electrons are going this way, and some of your electrons are going to go this way. Some of your coulombs are going this way, some of them are going to go that way. How many depends on how difficult the path is, right? If this is a difficult way to travel, you're going to get less coulombs traveling that way. If this is an easy way to travel, you're going to get more. take a look at our little river. If I suddenly make this really wide and make this bit really narrow, okay, that's going to completely change what's going on with our little river system. Suddenly, we're going to get an awful lot less water funneled down here and an awful lot more water funneled down here. Okay, and electrons traveling through a wire behave very much like water traveling down a river. Okay, so what we've got is we've got a choice. We've got kind of this junction here. Some water's going this way, or some electrons are going this way, and some are going this way as well. Okay, so how much is the question? Well, remember we said these two resistors are identical to each other. So basically what I've got is I've got a split in my river that's equally sized both ways. So I'm going to get half of my coulombs will go this way and half will go across the bottom. All right. If half of my coulombs travel that way, it seems reasonable to say that I'm going to see half as many of them every second. So here there's half as many coulombs per second. And remember, a coulomb per second is an amp. So up here we had 0.5 amps. That meant I had half a coulomb every second passing through here. There's going to be half as many as that again here. So this leaves us with this point giving me 0.25 amps at that point. And since once they get into that little bit, they have no choice. If it's 0.25 amps here, it's going to be 0.25 amps here, which is the reading on this ammeter. And the same would be true with an ammeter put here to be 0.25 amps all the way along here. And then when they meet back up again, it goes back up to 0.5. Okay, so your current splits and then comes back together. And that's what I mean. That's why I is the symbol for current, because it's the intensity, how fast your flow of water is, how much water have you got coming through here. Well, you only get half as much coming through here. So I halves, the intensity halves. It's carrying the same energy per coulomb, but you're getting half as many coulombs. Is that all right? Good, good. Okay, so get rid of our little river and reset our diagram, and let's see if we can really play with this idea a little bit further. Let's make something properly complicated. So let's get this moved over here. Let's extend this out a bit. We want to move our voltmeter. We're going to move our voltmeter up to here. Get rid of that. Get rid of that. We'll keep our little 0 volt one because that's useful. Okay. And this time, let's say that we have, let's say we have this going on. Okay. Again, we're going to keep these resistors identical. We're not going to deal with. We'll deal with doing calculations for this in our next live stream. We've only got 7 minutes left, and there's probably not enough time to cover that adequately. All right. But we're going to put an ammeter here. I'm going to shrink my ammeter down a bit. Okay, so we're going to put an ammeter here. I'm going to put an ammeter here. And we are going to put an ammeter here to let you know what's going on to start with. I'm going to stick an ammeter over here for fun. And we're going to have 1 voltmeter because the other stuff's not very interesting. This voltmeter is interesting. All right. Now, if you're doing double award, this is basically as tough as it's ever going to get. If you're doing triple award, you can maybe stick another resistor up here later on. But again, the process is pretty much the same. All right, change up our battery. Let's call it a 12 volt battery for this one. Okay, so we're going to come out with 12 volts. Again, just for the sake of making the numbers different, so you're not thinking, oh, wait a minute, did not see that number before. And let's give ourselves a current of 0.3 amps for reasons that will become quite clear quite soon. All right, so let's deal with the voltage first. All right, off we go with our 12 volt little coulomb, and he arrives down here, and that's the first time that we have to think about anything. So he's 12 volts down here, and our 0 volts comes round to here without having to do any form of thinking, because all the rest of this stuff may as well just not be here. Right, options time. If I travel across this way here, I'm only going to ever go through this resistor, and I have to arrive back with 0. Right, result 12 volts for this resistor. Right, not interesting because voltage across each parallel branch is the same. Right, nobody cares. The game gets interesting when I go here though, because I have to come through this resistor and through this resistor and then out with 0. And this behaves as a series circuit. because I have to experience the same thing. I have to experience the same energy loss going through here as I do going through here, because these are identical resistors and I'm traveling through them both one after the other. So the result is that I'm going to go in here with 12, come out here with 0, have the exact same experience in both. The result is then that this is going to be 6 volts lost, and this is going to be 6 volts lost. Alright, so the reading on my voltmeter is 6 volts, because it's only telling me what's going on between here and here. So I go in here with 12, come out with 6, go in here with 6, come out with 0. The change is 6 volts. Wait a minute, I hear you cry. Voltage across each parallel branch is the same. How can it be 6 and 6 and 12? Because 6 and 6 is 12. Alright, across each branch, I went this way and lost 12 volts. I went this way and lost 12 volts. Regardless of the option I took, I lost 12 volts. Just how I lost it was different each way. Alright, now current, little bit different this time. Alright, so let's imagine, let's see if I can get a little arrow. Let's imagine I have an arrow of this length that represents 0.3 amps. Okay, my little arrow comes down here, turns the corner, and arrives here. Alright, now you've got a water situation where you've arrived at a junction. Some of your water is going this way, some of your water is going this way, but it's not going to be 50-50. I'm going to get rid of these extra coulombs here. Okay, it's not going to be 50-50 because this top path is twice as difficult to get through as this bottom path. Thinking water, this stream is twice as narrow as this one. Alright, so we're going to split, we're going to ratio it in terms of difference. This is 2 times as hard, so 2x difficult. And this is just 1 times difficult. So I have a 2-to-1 ratio. Alright, 2-to-1 ratio of difficulty. But water doesn't care about difficulty. It cares about what the easier path is. You're going to get more on the easier path. But we'll talk about that in a second. There's a 2-to-1 ratio, which therefore means we have 3 parts. So our current's going to be split up into 3 parts, 2 parts going one way and 1 part going the other way. Which is why I did 0.3, because if 0.3 amps equals 3 parts, then 1 part equals 0.1 amps. Alright, and of course 2 parts equals 0.2 amps. Alright, so we know that one way it's going 0.1 and the other way is 0.2. We've worked that out. Now which one is it? In the bottom section, it's easier. It's twice as easy. If it's twice as easy, I'm going to get twice the intensity of electricity through it. Therefore, I'm going to get twice as much current. Therefore, I get 0.2 amps down here. All right. Up this way, I get the remainder. I get 0.1 amps up this way. Are we happy with that? Okay. And our little coulombs will flow on. Okay, so it'll flow through here like this. I will change the color of that so that you can see it. That's bound to be bad me on the, there we go, kind of a bluey color. Right, but we will also get current that travels this way here. So up here and then across here and then down. The critical thing though is at this point, that I'm circling here, at this point here, the whole thing comes back together and all travels along as it did before it came in, as a single unified current all the way up to here, given a reading on this ammeter of 0.3 amps. Okay, so our final rule then for parallel circuits is 2, that current is split between branches depending on the difficulty or resistance of each branch. right? And it's a little bit counterintuitive because the ratio is the other way up, okay? That it's 2 to 1 resistance, so it's 1 to 2 current. All right, so thank you very much for tuning in, everybody. It's 9:30. In 2 weeks' time, we will do the calculations for working out actual resistances here and whole scale stuff, and we will then be finished with circuit electricity. You should be able to deal with basically any circuit you get given in GCSE Physics. Thank you so much for tuning in, and don't forget, physics rocks. It's true.